the exercise problems of units and measurement, class 11th, subject physics. Question number 2 in that sub question 1. First question, it says that a star A is farther than star B, which star will have a large parallax angle. So this is our question number 2 in that sub question 1. So here is the diagram. This small d indicates it is the diameter of earth. In parallax method we observe stars from two different positions of the object, and apparent change in the position of that object, that method is called as parallax method. So here the star is observed from these two positions, let us say P and Q, that is these are the two diametrically opposite points observed from the earth, the star A and star B. These two stars are supposed to be observed. In the example it is given that star A is further than star B. It means that star B is near to the earth and A is little away from the earth. Therefore, the angle made by star A with the diameter of earth, it is theta A, and its distance from either of the positions on the earth's surface, that is big dA. Similarly, another star B which forms an angle theta B with the diameter PQ of the earth, and dB is its distance from the earth. Here in this example it is clear that small d is constant, that is diameter is constant. So what varies with the angle is the distance, or what varies with the distance is angle. Therefore the relation between angle and the distance between star and the planet, it is inversely proportional. Therefore theta B is directly proportional to 1 upon dB. On generalizing this equation, let us name it as a star, and for star A its parallax angle is theta A, which is directly proportional to 1 upon dA. Let's number this as equation 2. Here in this case, as dA is greater than that of dB, and from these two equations we can write it as theta increases, angle distance d decreases, or distance d decreases, theta increases. Therefore from this relation it is clear that more the distance, lesser will be the parallactic angle. So parallax angle is, we are asked which star will have a large parallax angle, right? So as distance dB is less, therefore theta B is more. Therefore theta B is greater than theta A. This is question 1. Question number 2, sub question 1. Now let's do it. Sub question number 2 from the question 2. In this example, what is asked? Let us read it. What are the dimensions of quantity small l square root of L upon G, where L being the length and G being the acceleration due to gravity? So let's do it. We are asked to find the dimensions of this term, L into L by G, where L is length. It has a dimensions L raised to 1. Small g, it is acceleration due to gravity, and its SI unit is meter per second square. Therefore the dimensions are L1 t raised to minus 2. Putting in this equation we get, let me first of all write the given equation L into square root of L upon G. Substituting the dimensions L raised to 1, acceleration due to gravity L raised to 1, T raised to minus 2 into outside the square root, it is L raised to 1. Now cancellation, this numerator L raised to 1 cancels with the denominator L raised to 1, and this T raised to minus 2 shifting to the numerator, it becomes plus 2. Therefore, this will be T raised to 2 into L raised to 1. Therefore, it will be L raised to 1 T raised to 2 raised to half. For this square root, we can write it as half. On simplifying, we get L raised to 1 T raised to 2 into 1 half. This 2 get cancelled. Therefore, this will be L raised to 1 T raised to 1. Therefore, the dimensions of term L square root of L by G are L raised to 1 T raised to 1. Next question. It's given that derive the formula for kinetic energy of a particle having mass m and velocity v. We are given dependence of the kinetic energy, and which is kinetic energy is dependent on mass. We don't know power of this mass, v raised to b. On observing this proportionality sign, we will express it in terms of constant of proportionality. Therefore, kinetic energy is equals to, let us assume this constant of proportionality as k m raised to a v raised to b. Let us number this equation as 1, where k is constant. Therefore, first of all, let us write the dimensions of all the quantities. Kinetic energy, it is SI unit is joules. So after expressing it in terms of fundamental quantities, the dimensions of kinetic energy are m1 L2 T raised to minus 2. Mass has dimensions m raised to 1, and velocity has a dimensions as it is meter per second. Therefore, it is L1 T raised to minus 1. Put all the things in 1. Therefore, on substituting it in 1, we get m1 L2 T raised to minus 2 equals to k L raised to 1 a L raised to 1 T raised to minus 1 raised to b. On simplifying, we get L raised to a 1 into a, that is L raised to a. L raised to 1 into b is L raised to b, and T raised to minus 1 into b is T raised to minus b. On writing in the simplified form, we get this equation as m1 L2 T raised to minus 2 equals to constant. It is L raised to No, it should be, I'm so sorry. This should be, it shouldn't be a length term. This is mass term. So let us write this.